All right, so we've done Taylor and Maclaurin. That tells us that we know how to find the power series now. Question is, what good are they and how can we use them? So we did one example last time. And for completion, let's start with the first problem on this packet, the application of series. And it's basically just a proof that series do work. So it tells us that sine is equivalent to this summation. And they want us to approximate sine of the square root of 5. And it asks us to use 3 terms, 6 terms, and then 10 terms. So I'm just going to write out all 10 terms, and then we would just plug in square root of 5 in each one of them and see what that gives us. So sine of x, first 10 terms, plug in n equals 0. So negative 1 to the 0 is 0, or sorry, 1. X to the 2 times 0 plus 1, so that's x. And then 2 times 0 plus 1, that's 1 factorial. So the first term is just x. Then you plug in n equal 1. So that would be a negative term. Plug in n equal 1 here, and you have x cubed. And then down here, 3 factorial. So I'm just going to write out the rest of the terms. So this would be 5 factorial, then minus that term. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's the first 10 terms. All right there. So then part A says use these 3 to do a calculation. So if you let x equal square root of 5, this comes out to be about 0.838525. If you use the first 6, which is part B, then you get 0.786744. And if you do all 10, so part C is 10 terms, then you get 0.786749. And if you approximate this with your calculator, the sine of square root of 5, you get exactly this number. So these 5 decimal places. So this is just a way to say, look, here is the power series for sine of x. If you want to approximate something like square root of 5, you need at least 10 terms to get 5 decimal place accuracy. And then it just says compare the values. So that would just be an exercise of using percent difference. So you would use the actual minus the experimental divided by actual, absolute value times 100%. So if you try to do that on this last one, if you did it to 5 decimal places, you'd get 0. Any questions about that guy? Should be pretty straightforward. Alrighty. That's just as bad. Let's just be that marker. So then I wanted to do the other example of integration. This example is for cosine. It is the integral from 0 to 1 of the cosine of the square root of x dx. Excuse me. So I asked someone yesterday how to go about solving this, and I was thinking about it myself. Off the top of my head, I don't know the most effective integration technique that we learned that we could possibly use here. So, in fact, this is a really good problem for us to apply these approximations. So in order to do this, we've got to use the fact that cosine of x is a summation from 0 to infinity. There's going to be an x to the 2n. It's going to be a 2n factorial. And there should be a -1 to the n in here. Now, there's two ways you could go about doing this. You could write out the first 6 terms with this series and then replace the x by square root x. Or we could right off the bat replace this x with square root x, then write the first 6 terms. So I think that's what I'm going to do. So this would become cosine of the square root of x, which if I plug that in now, would look like this. And we can simplify that because the square root of x to the 2n, well, square root is like x to the 1/2. So this 2 and the square root will cancel. Okay. So now let's write out the first 6 terms for that series. N equals 0, plug that in. Negative 1 to the 0 is 1. X to the 0 is 1. 0 factorial is 1. So the first term is just 1. Then n equal 1 is going to give us a negative x over 2 factorial. Next one's going to be plus x to the second over 4 factorial. And let me just write the next couple. So 1, 2, 3, 4, 5, 6. So this represents the first 6 terms of the series representation of cosine of the square root of x. We're going to use these to plug into the integral. So this integral equals the integral from 0 to 1, all of this dx. And this is great because polynomials are really easy to integrate. So this is just going to be x squared over 2 factorial, x cubed, sorry, this is going to be x squared over 2 times 2 factorial, right? Because there was already the factorial down there. When I get a 2 up here, I get a 2 on the bottom. So this will be x cubed over 3 times 6 factorial. And this is a plus, yeah, this is minus. This one becomes x to the 4th over 4 times 6 factorial. This one becomes x to the 5th over 5 times 8 factorial, and then finally x to the 6th over 6 times 10 factorial. And this all has to be evaluated from 0 to 1. Which really means we just have to plug in 1. So doing that, we have 1 minus 1 over 4. This is going to be 1 over, that is 72, I think. Let me check myself. Yep. The next one is 4 times 6 factorial. That is 1 over 2,880. Next one's going to be 1 over 5 times 8 factorial. I believe this one is millions. That was 21 million. 6 times 10 factorial. I probably didn't think it was going to be that big. So we'd have to add up all those, and I've already done that. Please check my answer. I get 0.764241 for the approximation. And if I were to plug this into the FNINT function, I get 763547. So not so bad, considering that integral is something that we're not too familiar with, right? You got something different for which part? I'll go ahead and redo it. All right, let me recalculate it. That was the number I had in my notes, which I may have gotten from someone else in class once before. We all know how troublesome it is to plug something into a calculator. Alright, so yeah, I see 76 3546, which is almost exactly the same as that, so that's even better, right? See, I don't know what that oh, I know what that number was. On my paper, I accidentally carried this out one more term. Which would have added back onto it. That was why. Alright, because these are alternating. Alright, are we all good with that one? Okay, good. So let's finish up this section. The last part asks us to now use these summations for some limits. So these limits that we're going to look at could be solved using L'Hopital's rule, or you could use this approximation method and get the solution. So the first one is limit x approaches 0, sine x minus x over x cubed. So I'm hoping that you guys have looked at or are planning to potentially print out the Power Series paper that I put up for you, the one that says Common Power Series. The reason is it's got sine in there for us, if you haven't already memorized it. So it should look like that. And if I were to write out the first couple terms, that would be x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So when I look at this limit, like as I said, if we plug in 0 here, sine of 0 minus 0, that's 0, and 0 cubed, still 0. So we could use L'Hopital's rule there, but instead, if I replace all of the functions that are not polynomials, then I can use this power series representation to do that and eliminate everything that I don't want. So the only thing here that appears that's not polynomial is sine of x. So I'm going to replace sine of x by these three terms. So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, all minus x over x cubed. So very easily these two x's here on the ends will cancel. I then am left with this. And what I'm going to do here is I'm going to divide each one of these by x cubed. So x cubed divided by x cubed is going to become 1. X to the 5th divided by x cubed is going to become x squared. Now if I were to apply the limit, this has nothing to do with x, so it's just going to stay itself. This term is going to go to 0. So I am left with minus 1 over 3 factorial, or minus 1/6. So here's a good question for you. This series is infinite, right? It's got an infinite number of terms. How did I know that taking the first three terms would be good enough? Any ideas? So yeah, the denominator here is x cubed, right? So I knew that when I started dividing them through, any of them that were powers higher than x cubed would stick around, and all of them would go to 0. So if I took any more terms, they'd all go to 0 anyway. So I really just, in fact, I really only needed the first 2, but I took 3 of them just to demonstrate. So I think a general rule of thumb, again, is to take about 3 terms to see what happens. Alright, the last one here says limit as x approaches 0 of x squared e to the x all over cosine x minus 1. Again, if we plug in, we get 0 over 0. Which is an indicator that we could use L'Hopital's rule, but we don't need to do that. So, what am I replacing in this limit with its power series representation? So I do need to replace cosine. Good. Anything else? E to the x. Good. So we need the first couple terms of cosine, which are 1 minus x squared over 2. And then that would be plus x to the 4th over 24 if we go out 3 terms. And e to the x is x, or sorry, 1 is the first term, plus x squared over 2. Alright, so let's plug it all in. So we have limit x approaches 0. We have x squared times 1 plus x squared over 2 all over 1 minus x squared over 2 plus x to the 4th over 24 minus 1. So again, your first instinct might be to multiply this x squared in everywhere, but that's actually not a good choice. I'm going to eliminate these 1s. And then what I would like to do is I see there's an x squared out here, and I know that both of these have x squared in them. So I'm going to factor out an x squared in the bottom. That way I can cancel those. That leaves me with this. Now again, limit as x approaches 0 means any term that has x in it, at least in the numerator, is going to go to 0 here. So I'll just be left with these first 2 terms. And again, the same process follows. If I had taken any more terms, they would all just go to 0. So the amount that I have there is fine. Another thing to take away from this is it wouldn't make a whole lot of sense to use really this only works for limits as x approaches 0, right? Or at least it's most effective in that situation. I don't believe this will work at all for if we're going towards infinity. So any questions about the problem or any of those either of those two problems? And again, you can find the power series on Blackboard. Excuse me. It's under, I believe, a section called Useful Papers. So, if you guys don't have any more questions about these, I'm going to go ahead and stop the recording for the day. And if you would like, we can go over the quizzes.